Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 13 of Algebraic Topology. In last lecture we saw some examples and we see that how to calculate the simplicial homology in that non-trivial examples. So we also observed a simple observation about calculating the simplicial homology of for example a simplicial complex, or in general we saw the following proposition, that if we have a simplicial complex and there exists this special vertex W of K with the property that if we have some set of vertices spanning Q simplex in K, then by adding W to that set of vertices we have a simplex of K as well. Okay, so if this is the case, then the simplicial homology of the simplicial complex, so H naught of K is isomorphic to Z and HQ of K is 0 for all Q greater than 0. So in this lecture we will see the proof of this result, and apart from that we will see the connection between H naught of K and connectedness. So in last lecture we used a simple fact that H naught of K is related to the path connectedness of this simplicial complex. So in this lecture we will see the results and we will prove the results. Okay, so let's start with the first part of our lecture, so proving this proposition. So as an important consequence of this proposition we have this result, that if we have a simplex, then for this simplex delta, let's say of dimension Q, then H naught of delta is isomorphic to Z and HQ of delta is equal to 0 for all Q greater than 0. So before proving this proposition we need this following lemma. So if we have a simplicial complex and G be a group under addition, and if we can associate with each Q plus 1 tuple, okay, so with each Q plus 1 tuple we can associate an element of this group G such that the image is 0 whenever we have repeated vertices, and this image changes signs or on interchanging any two adjacent vertices. Then there is a well-defined homomorphism from CQK to G, okay, which satisfies these two conditions. Moreover, this homomorphism is uniquely determined. Now we have a way of associating a Q plus 1 tuple with an element of G. Now we can extend this to a linear, so basically an integer combination of Q plus 1 tuples. So for example, if we have tuples, so the first one is V0, V1 up to VQ. So to differentiate between two tuples we have this superscript. So if I write down these ones and these twos, then these two are different Q plus 1 tuples, and if I have a combination of these, so for example N1 into this tuple, N2 into this tuple, up to so on, and S into V0 S up to VQS, then I can extend this this F, this way of associating a Q plus 1 tuple to any element of G to this integer combination of Q plus 1 tuples. So in this way that F is acting in a linear way. Okay, so linear means, so I can take out these coefficients and F is applied on this. Okay, so if I apply F on this thing, then in the first step I can write it down as F1 N1 V0 up to VQ1 plus N2 F of, okay, so I can take out this integer N2 as well. Okay, first I distribute this F on the addition of these elements, and then I take out this integer outside F. Okay, so that's what it means that we are extending F by linearity. Okay, so I'm sure now you can write down V02 VQ2, so up to so on ns f of v naught s up to vqs. Okay, so that's our extension. Now we know that CQK is basically a collection of all q plus 1 tuples, sorry, a collection of all q tuples under some conditions. So now, before extending or relation f to CQK, let's remind ourselves the definition of CQK. So this is basically the collection of all q plus 1 tuples, and these elements of the tuple are vertices of K, and such that we have the following conditions. So under these conditions, so under the first condition, it says that if I have an element of CQK, so let's say P0, P1, PQ, so Q plus 1 tuple, such that P0 is equal to P1, then this implies that P0, P1 up to PQ is a zero element in CQK. Okay, because we have taken quotient and we have this relation inside CQK. So under this relation, this is a zero element. Similarly, to see this second case, let's take Q is equal to 2 in particular. So P0, P1, P2. Okay, so let's use the following permutation. So 0, 1, 2. So 0 goes to 1, 1 goes to 0, and 2 goes to 2. Okay, so under this permutation, so this is pi. So what is pi of 0 is 1, what is pi of 1 is 0, and what is pi of 2? It's 2. Okay, so this is equal to p pi 0, p pi 1, p pi 2. So pi 0 is 1, pi 1 is 0, and p pi 2 is p2. Okay, so we can see that this 1 2 is fixed, so this permutation is nothing but 1 0. Okay, so we can see that this is an odd permutation. In other words, if I write down this permutation as product of transpositions, so transposition is a cycle of length 2, so if I write down this permutation as a product of transposition, so this permutation is written as one number of transposition. So in other words, this is an odd permutation. So we can say that this change will create the following difference. So this is after the permutation and this is before the permutation, so this is equal to minus of this thing, or this is equal to minus of this thing. Okay, so that's our second thing. Okay, so in other words, we can say that P0, P1, P2 minus, okay, so plus P1, P0, P2 is also a zero element in CQK. So in this case, we have taken Q is equal to 2. So these are the relation in CQK. So in other words, if we want to extend this F, which we have extended this, which we have, so first we extended this F to Q plus 1 tuples. Now we want to extend this to CQK. So what's the difference between Q plus 1 tuples and CQK? So CQK is collection of all generated by all Q plus 1 tuples together with some relations. So we just want to confirm that this F, this association of F with the so it associates Q plus 1 tuples with elements of the group G. So this association respects the relations of CQK. Okay, so in other words, if we have an element whose vertices are repeated, which will be 0 in this CQK, so this F takes that 0 to 0 of G. Okay, so similarly, if we have another element, so P0, P1, PQ, which is equal to signature of pi, and with this element, so F also respects this second condition of CQK as well. So this is more or less very obvious because we have already imposed these two conditions on F. So the first condition is trivially true. So we have already imposed that whenever two vertices are repeated, then this is equal to 0. So the first condition of CQK is satisfied. So f of V naught up to VQ is equal to 0 whenever two vertices, of course two or more vertices are repeated. Okay, so what about the second condition of CQK? So we have another relation inside CQK. So whenever we have a permutation of the vertices of this Q plus 1 tuple, then it is the same as multiplying the new tuple. So after permuting we have this tuple, and so if we multiply this permuted Q plus 1 tuple with the signature of pi, then it is the same as the original tuple. So once again this is clear because of the fact that every permutation can be written as a product of transpositions. So for example, if I have a permutation, let's say A1, okay, so A2, A3 up to AN, then I can write down this permutation as the product of transpositions A1, A2, A2, A3 up to so on AN minus 1, AN. Okay, so due to this fact, and so if I interchange any two vertices in this Q plus 1 tuple, so using this fact and using the condition on this F, that this will change the sign on interchanging any two adjacent vertices. So using this condition and using the fact that any permutation can be written as product of transposition of adjacent vertices. So if you combine these two conditions, then we will get the following, that f of any Q plus 1 tuple, so V naught up to VQ, and minus the signature of permutation pi, and V of pi naught up to V pi Q. Okay, so this is equal to 0, or in other words we can say that f of V naught up to VQ minus, so signature of pi, f of V pi naught up to V pi Q is equal to 0, or they are equal to each other. Okay, so once again, what was the second condition? So second condition on f is, if we permute any two adjacent vertices, then it will give me a negative sign. Okay, so this signature of pi is making sure that this expression is equal to this expression. So if these two are equal, then we can go opposite way. This is equal to this, and that's the condition that we require. So in other words, this f respects the relations of this free abelian group CQK, and there are only two relations in this. So if the vertices repeat, it gives me 0, and the second condition is on the permutation of the vertices. Okay, so these two conditions are satisfied, and so we have a well-defined unique homomorphism from CQK to this additive group G. Okay, so let's see the proof of our main proposition. Okay, now using above lemma, we define a homomorphism from CQK to CQ plus 1K. Okay, so with the following property. So if we have a Q simplex, so an element of CQK, then after applying this DQ, we just add W to this Q simplex. Of course, when we add one more vertex, then it is an element of CQ plus 1K. Okay, so now we have the following image of the situation. Okay, so what's the image? So if I have a 0 simplex, then I can get from this 0 simplex a 1 simplex. If I have a 1 simplex, then I can get a 2 simplex, up to so on. If I have a q simplex, then I can get a q plus 1 simplex. And we already have this chain complex as well, which is defined by these boundary operators. Okay, now what is d naught of v? Okay, so d naught of v, so according to the definition, we just add w on the extreme left side, and so this is equal to wv. Now we want to calculate the boundary of this new element, which is d naught of v. So this is equal to boundary of this element wv, and according to the definition, this is just equal to v minus w. Okay, so basically v minus w. Okay, now we claim that an element of c naught of k belongs to b naught of k if and only if the sum of the coefficient is 0. Okay, so the forward part is easy. So why it is easy? So if you take basically an element of c1 of k, so what are the elements of c1 of k? So let's just say that they are 1 simplices. So for example, take an element v naught v1, take another element v2 v3, take another element v4 v5, and up to so on. So consider this combination now. Okay, so a naught v naught v1 plus a1 v2 v3 plus a2 v4 v5. Okay, now calculate partial 1, the boundary of this. So let's just concentrate at the first term. So this becomes, so v1 minus v naught. Okay, so what is the sum of the coefficients? So the coefficient of v1 is basically a naught, and the coefficient of v naught is minus a naught. So the sum of the coefficient is 0. Similarly, in this case the sum of the coefficient is 0, in this case the sum of the coefficient is 0. So in general we can say that in b naught the sum of the coefficients is always 0. Okay, so in the elements of b naught, which are image of the elements of c1 of k, so we can always observe that the sum of the coefficients is always 0. So the forward part is easy. So in general we can show it as well. I mean, we can write it as well properly. So now conversely, if we have an element of c naught of k, so the elements of c naught of k will be of the form nr pr, where r is equal to 1 to s, and this c naught, we are assuming that this c naught k is generated by these s vertices of the simplicial complex k, and the general element will be of this form. Now if we assume that the sum of the coefficient is 0, then we have the following picture. Okay, if the sum of the coefficient is 0, then basically this expression is equal to 0. So basically with every element nr pr, where r is equal to 1 to s, we can add this term, and it will not make any difference because this is just 0. Okay, so with this vertex w. Now this expression can be written in the following form. Now take the first element from this expression and take first element from this expression, so we get v1 minus w1, and the coefficient of w1 is n1 and coefficient of v1 is n1, so we get n1 v1 minus w. Okay, so similarly I can do it for the second term as well. So plus n2 v2 minus w. Okay, so when we have done this, then we can write down in this summation form, and since this v1 minus w is basically boundary of a one simplex. So what is this boundary of? So basically I can write this down as, so I need the first vertex to be W and the second vertex to be V1, so that the boundary of this thing is ignore W, we get V1, ignore V1, we get W. So basically this is equal to partial 1 of this element, so n1 partial 1 of this element. Okay, so basically this is equal to n1 partial 1 of W1 V1 plus n2 partial 1 W V2 up to so on. Okay, and then this partial 1 is basically homomorphism, so we can take common all these things. So in other words, we can write down partial 1 n1 W V1 plus n2 W V2 up to so on, so plus s terms. Okay, so the sth term, and so this is basically a general element of S1, and this is image of that general element of C1. Okay, so this is general element of C1, and partial 1 is the image of that general element. Of course, the image of partial 1 is basically B0, so that's why this is an element of B0. Okay, so we have proved that an element of C0 of k belongs to B0 of k if and only if the sum of the coefficient is 0. Also, Z0 of k is equal to C0 of k. Okay, so why is that the case? Because C0 of k goes to 0 under this partial naught, so everything from this free abelian group goes to 0, so that's why Z0 of k is equal to C0 of k. Okay, so now consider the following homomorphism. So it takes elements of C0 of k and it gives me the sum of the coefficients. And now according to the little result that we have proved that an element of C0 of k belongs to B0 of k if and only if sum of the coefficient is 0. So we can see that the kernel of alpha is equal to B0 of k. Okay, so by using first theorem of isomorphism, okay, so this is isomorphic to Z because this is an onto homomorphism. Okay, so C0 k quotient B0 k is isomorphic to Z, so C0 k is basically Z0 k, so Z0 k quotient with B0 k is isomorphic to Z, and this is in fact H0 of k. So H0 of k is basically Z. Okay, so now we have calculated H0 of k and it becomes Z. So now consider the case when q is greater than 0. Okay, so consider this expression. Okay, so take an element of CQK. Okay, so remember that we have two way. Okay, so we can go from CQ minus 1k and CQ plus 1k. Okay, so this is the boundary operators, okay, up to so on, and on the other hand we have the following thing as well. Okay, so CQ plus 1k, so on the other way we have this DQ, so which takes an element of CQ of k and it gives me an element of CQ plus 1 of k. Okay, so how do we do that? So we just add W on the extreme left side and it will give me a q plus 1 simplex, and when we apply the boundary operator on this thing, then of course this is again an element of CQK. So we start from an element of CQK, apply DQ, gets an element of CQ plus 1k, and then apply this boundary operator and gets again an element of CQK. Okay, so by using the definition of boundary, so if we ignore the first element, which is w, then we will get minus 1 raised to power 0, and just delete w from it. Okay, and going on, we just need to delete this vertex, so from v0 to vq. So when you delete one vertex, then you multiply it with minus 1 raised to power j plus 1. So why j plus 1? Because we have included this w on this side as well, so I need to add 1 on each and every for each and every vertex. Okay, so now I can write down this plus 1 over here. Okay, so minus 1 raised to power plus 1 can be written here, and we get minus 1 raised to power j and this. Okay, so what is this expression now? Okay, so what is this expression? So this expression is basically, first you calculate the boundary of v0 up to vq, and then you add w to it. Okay, so basically what is the boundary of v0 up to vq? So if you just ignore this w from here and just delete it from this expression, then this thing is basically, so this expression is basically the boundary of v0 up to vq. But then what do? We just add w on the right side, because we are operating dq minus 1 on this thing. Okay, so basically we started from this expression and we ended up at this expression. Okay, so in other words, we have the following thing, that for any element c of cqk, apply dq on c and then calculate its boundary, or calculate its boundary first and then apply dq minus 1, then this is equal to c. So the sum of them is equal to c. So now in particular, if we have an element of zq of k, so of course what is the definition of elements of zq of k? The image under partial q will be 0. In other words, this expression becomes the following. So partial q plus 1 dq z, so there will be no change in this expression, plus dq minus 1 partial q of z equal to z. Okay, but this thing is 0, so we get the following thing, that z is equal to partial q plus 1 dq z. Okay, so z is equal to partial q plus 1 dq z. So we have this expression for all z belongs to zqk. So every element, so from this we can say that every element of zqk is also an element of bq of k. So what are the elements of bqk? So the images of partial q plus 1. Okay, so the elements of cqk whose which are images under this partial q plus 1. Okay, so this element z, which is an element of zq of k, is also boundary of some element. Okay, so what is this element? We are not interested, but it is boundary, it is the image of some element of cq plus 1. Okay, so dqz is an element of cq plus 1, because z is element of cq, dqz, so dq will give me an element of cq plus 1, so this is an element of cq plus 1. Apply partial this boundary operator and you will get an element of cq. So we can say that in this case zqk is equal to bqk whenever q is greater than 0. So we can say that whenever q is greater than 0, then hq of k is equal to zqk quotient with bqk, and so these are equal, and so it is equal to 0. Okay, so we have proved this important result, that under some conditions, if we have a simplicial complex satisfying certain conditions, then the homology h0 of k is equal to z, and homology hqk is 0 for all q greater than 0. So in particular, we have already seen that if we consider a simplicial complex, then the homology h0 is z, and higher homology groups, so hqk are 0, So let's come to the next section of today's lecture. So H naught of K and connectedness. So as we used in last lecture that H naught of K represents the path connectedness of simplicial complex. So now we are going to prove the results, and we are going to see the consequences of this and the importance of this thing. Okay, so consider this one-dimensional simplicial complex. So in particular we have taken this graph. So what is a graph? A graph is a collection of we can say that a graph is an ordered pair where V is set of vertices, E is the set of edges, and if we consider the simple case when the edges are not multiple, in general there could be more than one edges between two vertices. But if we don't allow these multiple edges, then this is a simple graph. And also we are not including the direction. So for example, it could be directed graph as well. So once again, we are not including these directions as well. So in the simple case, when we have no multiple edges, no directions, and we have a simple graph, then this simple graph is a one-dimensional simplicial complex. Okay, and we will see that we can calculate the homology of this simplicial complex. Now let's see how to calculate the homology of this simplicial complex, which in particular we have taken to be a simple graph. Okay, so let V be the number of vertices and E be the number of edges. Then C1 of K, which is the free abelian group generated by the one simplices, or in other words the edges, is basically isomorphic to ZE because we have E number of edges. And similarly C naught of K, which is generated by the zero simplices or the vertices of this simplicial complex. So in this case we have V number of vertices, so C naught of K is isomorphic to Z raised to power V, or in other words V copies of Z, or it's a free abelian group of rank V. Now consider the following boundary map from C1 of K to C naught of K. Now we know that H naught of K is equal to Z naught of K quotient with B naught of K. Also once again in this case, so if you consider this C naught of K goes to 0, this is partial naught, so everything in C naught of K is going to 0, so that's why C naught of K is equal to Z naught of K. Also B naught of K is equal to image of this boundary map partial 1 of C1 of K. Okay, since the simplicial complex is path connected, okay, so we have taken this graph to be path connected. Okay, so it's not a disconnected graph. Okay, so that's another condition that we imposed. So if our graph is path connected, then the simplicial complex is path connected, and so H naught of K is equal to Z. Now we shall see the proof of this in our later discussion. So we are going to prove this result in today's lecture. So we are just using this result, and we will see that just using this result will also help us in calculating the simplicial homology. So we already know what is H naught, but this result, knowing this result will help us in calculating what is H1. Okay, so if H naught of K is equal to Z, and also H naught is equal to C naught K quotient B naught K. So Z naught K is equal to C naught K, so H naught is C naught K quotient B naught K. Okay, so and this is isomorphic to Z. But we also know that we have this boundary operator partial 1 from C1K to C naught K. So the image of this is B naught. Okay, so the image of partial 1 is B naught, so C naught K quotient with B naught K is isomorphic to Z, or in other words C naught K quotient image of partial 1 is isomorphic to Z. So from here we can say that since C naught K is of rank V, in other words isomorphic to Z, V copies of Z, so we can say that this image is isomorphic to VZ, so V minus 1 copies of Z. Okay, so now we know that H1 of K is equal to Z1 of K quotient with B1 of K. Now observe that using first theorem of isomorphism, so what is this theorem? We have this partial 1 from C1 to C0, and so C1 of K quotient with kernel of partial 1 should be isomorphic to the image of partial 1. So the image of partial 1 is isomorphic to Z V minus 1 or V minus 1 copies of Z. Okay, so so this is Z V minus 1. So what is this? C1 is basically isomorphic to E copies of Z. So that's why, so E, so minus something is equal to V minus 1. Okay, so E minus, let's say X, so this has rank E, we don't know the rank of this, so let's say the rank of this is X, so E minus X is equal to V minus 1, which is the rank of image of this partial. So what is this X? So X is equal to E minus V plus 1. So this is the rank of kernel of partial 1. So the kernel of partial 1 is isomorphic to Z raised to power E minus V plus 1, or in other words E minus V plus 1 copies of Z. So we know the rank of Z1 of K, which are basically set of elements which are going to 0. Okay, so if we know Z1 of K, now B1 of K is 0 because C2K is 0 because it's a simplicial complex of one dimension. So if this is 0, then the image of partial 2 inside C1 of K is 0. So the image of 0 is 0 in C1 of K, so that's why B1 of K is 0. And so H1 becomes this. So the rank of this we already calculated is this E minus V plus 1, and B1 of K is 0. So taking quotient, we get E minus V plus 1 copies of Z. So we calculate H1 of K. Okay, so we use this result, which we shall prove in today's lecture, and using this result we can calculate H1 of K in this simple example of one-dimensional simplicial complexes. Now coming to our main results. So before proving the main results, we need some little results. So our first lemma is, if we have a simplicial complex, then K can be partitioned into pairwise disjoint subcomplexes whose polyhedron are the connected components of the polyhedron, this the underlying space of K. Okay, so this underlying space of K, which is the simplicial complex, so this is a subspace of the Euclidean space, and so under the usual topology in the Euclidean space, we can say that this can be written as a union of disjoint union of basically its components. So this thing is basically trivial from the course of topology. So every subspace can be written as disjoint union of its components, but what is non-trivial about this lemma? So the non-triviality comes that now we want to write down any simplicial complex as a disjoint union of its subcomplexes. Okay, so that's what we want to prove. So now using the fact from topological spaces that this underlying space of a simplicial complex K, so this underlying space can be written as disjoint union of its connected components. Okay, so we can write this down as this, and now we define K1 up to Kn. So now we are going to define these K1 up to Kn in a way that is a simplex sigma of K belongs to Kj if sigma is contained in Aj. Okay, so it should be Aj. Okay, so of course if we have a simplex inside this simplicial complex K, then its underlying space will belong to the underlying space of K, and underlying space of K can be written as disjoint union of connected components, and so the underlying space of this sigma will belong to one of these AIs. So let's say that AI is AJ. Okay, now we define these K1 up to Kn in this way. Okay, so if a simplex sigma belongs to Kj, then all its faces also belong to Kj, because the faces of sigma also satisfies the same condition, that the underlying space of the face belongs to Aj. So that's why this Kj contains all its faces as well. So basically it satisfies the conditions of a simplicial complex. So that's why all of these K1 up to Kn are subcomplexes of K. Okay, so since the connected components are pairwise disjoint, so all these subcomplexes are also pairwise disjoint. So what is the underlying space of K1? This is A1. What is the underlying space of K2? This is A2, up to so on, and these AIs are disjoint, so that's why these K1 up to Kn are disjoint. If sigma belongs to K, then there is a unique J such that sigma belongs to, okay, so it should be Aj. So since Aj partition this space, this underlying space of simplicial complex K, and okay, so it should be A1, A2, An, okay, so A2, A3 up to A, n are pairwise disjoint, hence there is a unique Kj containing sigma. Okay, so if we have a simplicial complex, or if we have a simplex belonging to K, then its underlying space will belong to one of these AIs, and so that's why if let's say it belongs to Aj, then this implies this sigma belongs to this Kj, and this is unique Kj. It cannot happen that this sigma belongs to Kj and some other Ki as well. So this cannot happen because these AIs are mutually disjoint. Okay, so we can write down this K as disjoint union of subcomplexes. Okay, so it's a very simple result, and what we have proved in this result, so given any simplicial complex, it can be written as disjoint union of subcomplexes. Okay, so in this case we just proved a simple result from topological spaces, that every space can be written as disjoint union of its connected components. So using that and defining these K1 up to Kn and proving that they are in fact subcomplexes, or in fact they are, K1 is simplicial complex, K2 is simplicial complex, up to Kn is simplicial complex, and proving that, and then writing down and then showing that every simplex of K belongs to one of these Ki's. So in other words, this K can be written as disjoint union of these simplicial complexes or subcomplexes. Okay, so now let K be a simplicial complex, then of course this K can be written as disjoint union of its subcomplexes, and which are K1, K2 up to Kn, and these are pairwise disjoint as well. Now the next result proves that this HQK, so the Q homology group, is isomorphic to HQK1, so direct sum HQK2, direct sum up to HQKn. We know that if Q is greater than the dimension of K, then CQK is 0. So we have the following chain complex, so in this case this CQK will be 0. Okay, and from here we can see that the boundaries and the cycles are 0, so that's why HQK is 0. So now let's go on and prove this result for Q less than or equal to dimension of K and greater than or equal to 0. So if we have an element of CQK, then this can be expressed uniquely as C is equal to C1 plus C2 up to Cn. okay, where Ci belongs to CQKI. So this K can be written as disjoint union of K1, K2 up to Kn, and if I have an element of CQK, then since an element of an element of K either belongs to K1 or K2 or Kn, so this C which is basically an element of CQ of K can be written as this sum, where C1 belongs to CQ of K1 and C2 belongs to CQ of K2, okay, and up to so on, and this Cn belongs to CQ of Kn. Okay, so this K1 contains some Q simplices, this K2 contains some Q simplices, this Kn contains some Q simplices. So we are just saying that this C, which is the integer combination of these Q simplices, can be written in this way, and C1 contains the combination of Q simplices from K1, C2 contains the combination of Q simplices from K2, Cn contains this integer combination of Q simplices from Kn, because these K1, K2 up to Kn, these are simplicial complexes on their own. So that's why we can write down this element of CQK in this form. And from here we can say that CQK is basically equal to CQK1, CQK2, CQKn. Okay, so this CQK can be written as direct sum of CQK1, CQK2 up to CQKn. Now, if I have an element which is an element of CQ, which is also an element of ZQ of K, okay, so CQ of K, and so what are the elements of ZQ of K? So the elements which goes to 0 under this boundary operator partial Q. Okay, so if we have an element which goes to 0, which means this is equal to 0, and since every element of CQK can be decomposed, so we can write down Z as well. Okay, so because this is an element of CQ as well, and we proved that an element of CQK can be decomposed as sum of elements of CQK1, CQK2 up to CQKn, and so Z can be written as this way. When we apply this boundary operator partial Q on both of these sides, then partial QZ is equal to 0, because this is an element of ZQ of K, and using this homomorphism property of partial Q, so we get this expression. Okay, so it follows that this partial Q Zi are equal to 0. So this is 0, this is 0, and this is 0. So every element is 0. So in other words, we can say that this Z1 belongs to ZQ of K1, Z2 belongs to ZQ of K2, and Zn belongs to ZQ of Kn. So what is ZQ of Kn? So basically ZQ of K1 is contained in CQ of K1, and these are the elements which goes to 0. So partial Q of ZQ of K1 is equal to 0. Okay, so this is contained in CQ of K1. Similarly, ZQ of Kn is contained in CQ of Kn. Okay, so we can decompose ZQ of K as well. Now, if we have an element of BQ of K, once again this element of BQ of K is an element of CQ of K as well. So so basically B is an image of some element C of CQ plus 1 K. Okay, so this element C, which is an element of CQ plus 1 K, can be decomposed in this way. Okay, so where C1 basically belongs to CQ plus 1 K1, C2 belongs to CQ plus 1 K2, up to so on, and thus Cn belongs to CQ plus 1 Kn. n. And so we can decompose this element of CQ plus 1 in this way, and when we apply this boundary operator partial q plus 1, then we get this following expression. Okay, and now this element basically is image of element of CQ plus 1 k, because C1 belongs to CQ plus 1 of k, and so this boundary operator when applied on C1 will give me an element of BQ of K1, which is of course contained in CQ K1. Okay, so in this way, this is, let's say this is equal to B1, this is equal to B2 up to Bn. So this B can be decomposed as B1 plus B2 plus Bn, and this B1 belongs to BQ of K1. So BQ of K can also be decomposed in this way. Okay, so now we can define an isomorphism from HQK1 plus, so direct sum HQK2 up to so on HQKN to HQK, so taking Z1 Z2 Zn to Z1 plus Z2 plus Zn. Okay, so this is an isomorphism, and it's very trivial to see, and this proves our required result. So now we have another simple result. If we have a polyhedron of a simplicial complex, and which is okay, so this polyhedron is connected topological space if and only if any two vertices of K can be joined by an edge path. Okay, so this is the proof of this is very simple, but the result itself is very non-trivial, because over here we are relating. Okay, so if K is any simplicial complex, then we are saying that this underlying space K mod is connected topological space if and only if any two vertices can be joined by an edge path. Okay, so let's consider. So consider any two vertices of K, and if they can be joined by a path, then obviously this is path connected, and this way is very trivial. So on the other side, let's assume that this is connected. Now we have to show that this is edge connected as well. Okay, so remember that for any topological space we related path connectedness and connectedness, and we saw that they are not the same, and we have to impose some conditions on the connectedness to get path connectedness. Okay, but in this case, so as I said earlier, that this is a non-trivial result, that in this case the connectedness of this polyhedron is the same as some special kind of path connectedness. Okay, so now conversely, if this is connected, then we want to show that any two vertices can be joined by a path. Equivalently, we show that any vertex of K can be joined to a fixed vertex V0 of K. Okay, so instead of showing that any two vertices can be joined by path, we just show that any vertex can be joined with this V0, and of course if any vertex can be joined with this V0, so let's say this is V1, this is V2, V1 can be joined by some path with V0, V2 can be joined by some path with V0, then of course V1 and V0 are also can also be joined by some path. So that's our strategy. So let K0 be a collection of simplices of K having the property that if Q belongs to K0, then one vertex of the simplex Q is connected to V0. Okay, so we have taken the collection of all simplices of K such that one of the vertex of that simplex is connected to V0. So for example, let's say this is some complicated simplex, and this is connected to V0, and this K0 contains set of all simplices satisfying this condition. Of course, you can see from here that if one of the vertex of this simplex is connected to V, then all the vertices of this simplex are connected to V as well. Hence all the vertices of K are connected to V0. Okay, so it is clear that all the faces of simplexes in K0 also belongs to K0, because if if basically this simplex belongs to K, then its face also belongs to K as well, because the vertices of this face also are connected to V0. So K0 is a simplicial complex. Now let's take this K1, which is the collection of all simplices with the property that it contains all simplices such that the vertices of Q are not connected to V0. In this case, if let's say if I have some simplex and the vertices of this simplex are not connected to V0, then of course the vertices of its faces are not connected to V0 as well. So that's why this K1 is a simplicial complex. Okay, so if so all its faces, so all faces of any element of this K1 also belongs to K1, so it's a simplicial complex. Also this K can be written as union of K0 and K1, and their intersection is empty. So why their intersection is empty? Because K0 contains all those simplices which are connected, whose vertices are connected with V0, and K1 contains all those simplices whose vertices are not connected with V0. So their intersection must be empty. Also this underlying space of K is equal to underlying space of K0 union underlying space of K1. So where the intersection is equal to phi, which contradicts the connectedness of K. So either K0 is equal to phi or empty, or K1 is empty. But V0 belongs to K0, so K1 must be empty, because K0 cannot be empty, and one of them has to be empty. So we have a path between any two vertices of K. Now we have our result that we discussed throughout our lecture. If we have a simplicial complex and the underlying space is a polyhedron, and if it is connected, then H0 of K is isomorphic to Z. So we know that the connectedness of the polyhedron and path connectedness of the simplicial complex are equivalent according to our previous lemma, which says that the polyhedron of a simplicial complex is connected topological space if and only if. So logically they are equivalent if any two vertices of K can be joined by an edge path. Okay, so when we are assuming, when we are supposing that the polyhedron is a connected topological space, so in fact we are assuming that the simplicial complex, any two vertices of the simplicial complex can be edge connected. Okay, so there is an edge between any two vertices of this simplicial complex. So if this is the case, then H0 of K is isomorphic to Z. So the proof of this is provided in the lecture notes, and it's simple. Next time we will continue our discussion, and we will need some machinery from homological algebra, and we will review that machinery from homological algebra, and we will be using it with our homological calculations in our future lectures. This is the end of the lecture. Thank you very much, and Allah Hafiz.